and welcome to today's webinar. My name is Carla Lauder, and I am the editor of GeoWeek News. I first want to thank Intel Geospatial for their support of today's webinar, which, as you can see, is entitled Automating Lidar Workflows with AI. A very interesting topic today, but we have a couple of housekeeping notes to go over before we dive in. If you have any technical questions or issues using this webinar platform, you can use the chat box, which is found on the right-hand side of your screen, to message one of us and we will respond right away. If you have any issues with audio, there is also an option to click on a phone icon above that chat window and receive dial-in information so you can join via phone. For anyone who does call via phone, to ensure everyone's quality, everyone's lines are going to be muted today except for those who are speaking. However, we do want this webinar to be interactive, so we encourage you to ask questions. And the way that you do that, there is another box called the Q&A box, and that should also be on the right-hand side of your screen. And you can put your questions in there at any time during the presentation, and you can select all panelists when you do that. What we'll do at the end of the presentation is any questions that haven't been answered during the presentation, we will ask out verbally, and we'll have a Q&A time set aside at the end for that. So please feel free to put those questions in at any time, and we'll try to grab them at the end of the presentation. If you happen to get disconnected for some reason, you can log right back in using the instructions that you got via email. And if you continue to experience difficulty, you can email info@geo-week.com and someone there will help you right away. This webinar is also going to be recorded, and you will receive a follow-up email with the on-demand materials within 3 business days. So if you miss anything, you will have an opportunity to rewatch it. Today, we are going to be hearing from presenters from Intel Geospatial, and joining us today are Ophir Levy, who is the head of artificial intelligence, and Eric Whitner, co-head of product. And before I turn it over to our 2 speakers, just one last reminder to send in those questions at any time, and I'll be back at the end to run through those with our presenters. And with that, I'm going to turn it over to Eric to get us started.
Okay, thank you very much. As mentioned, my name is Eric Whitner. I am the co-head of product and head of data acquisition here at Intel Geospatial. And I'm presenting here with Ophir Levy, who is our head of artificial intelligence. And we wanted to talk to you about some of the work we're doing with artificial intelligence, specifically with Lidar and point cloud data. Intel Geospatial has a variety of experiences, really specifically in the energy and utilities sectors, using artificial intelligence to derive insight and answer questions for customers, doing asset inventory for electrical distribution and transmission, doing defect detection, doing vegetation encroachment analysis on electrical utilities, and also doing leak detection and severity scoring for oil leak detection and petroleum. But today, we wanted to narrowly focus on just the use of the point cloud data around this utilities model. And we wanted to go through some of the common challenges that our customers have been experiencing and have expressed to us, and that we're trying to help them solve, how we're solving those with artificial intelligence for auto classification of LiDAR data, and then vegetation encroachment analysis of the LiDAR data, and then just in general introduce you to the Intel Geospatial platform and how that's being used for LiDAR. So when we talked to our customers, when we surveyed our customers, there was a variety of key use cases that they wanted us to tackle. One is vegetation management around utilities, infrastructure, being able to understand where they actually had to do work, to do trimming and management in order to reduce risk. A lot of interest in doing digital twins and collecting 3D models for cities and urban environments for planning, infrastructure inspection, and operations and maintenance, as well as general location analysis and analytics. But the challenges were pretty common amongst all these different use cases. Doing analysis at scale, managing large volumes of data, the cost of doing all that, trying to turn raw data into useful data, the time that took, the time it took to turn that around into usable information, the ability to reuse processes that you've developed once multiple times, generally the accuracy and quality, and then actually building these really heavy data sets into the business workflows. So specifically, next slide, when it comes to the Lidar point clouds, there were some common business challenges. One is the variety of acquisition methods, manned aircraft versus terrestrial collection versus unmanned aerial vehicle, that drove a variety of different data sources, different capture angles, different intensities and colors that all need to be managed and put together so that you can use them collectively. The turnaround time that's involved in that, the weeks to months from collection to actually being useful data that you can work on in real time, then just managing these incredibly large data sets where, you know, a 1 mile section of an electrical transmission or distribution line at a 150-foot wide corridor can be 2 gigabytes. So you're talking terabytes and terabytes of information along these complex electrical networks. Being able to kind of bring together non-uniform formats into a single platform or a single layer that you can do comprehensive analytics and workflows on. And then classification, you know, requiring a lot of manual correction as you're working on through the classification. So we're focusing on trying to build a platform that can solve some of these problems and analytical tools that can ease the management, visualization, classification, and analysis of this data. So I'm going to turn it over to Ophir to talk a little bit more specifically about the analytics that we're building, classification, and vegetation encroachment.
Thank you, Eric, and hi everyone. So when we are talking about point cloud AI, AI on point cloud coming from Lidar, what we typically know from existing out-of-the-shelf software is capabilities that rely on classical algorithms that usually underlines some heuristics. For example, when we want to detect ground, we use plane detection. When we want to detect houses and buildings, we use multiple coplanar detection to identify roofs. There are other features that we use for wires, for example, linear features, return number of the LiDAR for detecting vegetation. And many of those heuristics actually required a lot of thresholds, like maximum height of the planar, the altitude, split it into different bin sizes, define the maximum bounds, the area bounds, and so on and so forth. So that's really one drawback of these algorithms. The other one is that they are not supporting they're supporting the basic objects, the ground, vegetation, buildings, so on, but they cannot detect other more sophisticated objects like cars, like lights, and so on. And we also see that even in the basic object, those because of these heuristics and those thresholds, they tend to be breaking in many cases. And we see from our experiences and our customers' experiences that running algorithms, automatic classification algorithms using these methods really requires many fixes afterwards, manual fixes. And if we think about those algorithms and compare them with what we have with the 2D traditional computer vision, so traditionally what we used to be doing is taking the image, the 2D image, and extracting its many features that has that will help us to get some understanding about what's going on in the image. Features like color histograms, the gradient directions and combination of the gradient direction, which leads us to more sophisticated features like SIFT and so on. So these are really the traditional, how we traditionally did computer vision and AI back then. And we look on what we have today. So today, almost all of our tasks on the 2D world and the imagery world are being solved by deep learning. And the deep learning is being trained end-to-end, and those features are being learned automatically and optimally for the task at hand. We're not doing it manually, it's completely automatically. And when we are looking on the features that were actually learned throughout the process, we see that they are very similar to what we were doing before deep learning area. Some things like color histograms, gradients, directions, and so on. And those features, so these are the low level, and then going to the mid level and high level, we see parts of objects, and then the objects themselves on the higher level features. So these features are being learned automatically and optimally for the task, whether it's cars or faces and so on. So we really want to use the benefit of the deep learning for the point cloud domain. And there have been some tries to adapt the point cloud into the 2D world. We can take a projection view of the point cloud, for example, bird eye view, and maybe more profiled view that being generated into depth map, and in that way we can to some extent use the point cloud and feed it as a 2D image. But there are methods that are using that, but what we really want to do at the end of the day is to leverage our point cloud as is and find networks that can handle this point cloud as is, as a natural input, and provide understanding out of that point cloud. So why is it so hard? Why is it only in the latest 1 or 2 years we start to see some progress, and currently out-of-the-shelf algorithms are not using CNN or any other networks to date? So there are a few challenges with processing, running AI, or training AI on point cloud. One is that the point cloud that's being fed in is usually very sparse. So we see areas where it's very dense, cases where it's vegetation, while other areas are completely sparse and sometimes have no points at all. So it's hard to feed this kind of structure into CNN optimally. The other one is that the point cloud are not structured, meaning that there is not a table or a grid that we can put the point cloud into, and there is no fixed distance between those points. And the third one is that the points are not ordered. There is no meaning to the order of the points. If we take one file with points P1 to P7 and we shuffle those points, we will still get the same point cloud. We'll still get exactly the same scene. So there is no meaning to the order of the points, and that really, those challenges make it very hard to feed it into a regular 2D or 3D CNN. It also causes our memory access to be very inefficient because we want to take a point with all of its neighbor and do some processing. We'll have to go and access different area on the memory, which causes very slowdown. And so before I'll talk about our AI solution, first let me talk about usages of why we want to run and train AI on point cloud. So the main usages that we see today, first is a very popular usage of vegetation portrait, which I'm sure most of you are aware of, and we'll touch on that later. Other than that, anything that involve accurate asset location and counting, having an inventory, because imagine that on the 2D imagery, we typically have multiple capture of the same object, but we really want to have accurate counting of the object. So the 3D point cloud really allow us to count accurately and also found the location accurately. Other than that, we have that allows us to have to measure the object size and volume very accurately and measure distance between objects very accurately. And also, if you want to use other usages that needs to have RGB in, then we can use sensor fusion to maybe do this semantic and the understanding and the recognition of the objects on the RGB, and then we can do other stuff like the sizes and so on. We can project the RGB into the point cloud, and then we can do the other use cases from there. And just to share some of the classes that we are looking in those usages. So these are really the popular objects that we see on the urban domain, starting with ground, sidewalk, road, coming to objects that are more specifically for usages like conductors and vegetation and any other popular common object on the urban, like car, buildings, traffic lights, and so on. And also, when we are talking about LiDAR and point cloud, I usually tend to divide it into three segments, three domains that one is the manned aircraft, I'll talk about in a second. The other one is terrestrial, and the third one is UAV or drone. Started with the manned aircraft. So what we were doing with Intel Geospatial, we have a collaboration with Veritas Data, which is a Geiger mode LiDAR plane that is flying above the clouds at very high altitude, can capture a large area very efficiently with high density of 30 to 60 points per square meter. And it doesn't have any RGB there, so it's intensity only, meaning that each point gets a gray level scale like you see here. So that's type of data that we use for recognition on and detect and classification on a very high scale, on a city scale. And what you see here is the results of our AI. So we took that data, we trained on that using a recent network that we took and further developed for our needs, networks that actually can take 3D point cloud, train on that naturally, and provide auto classification. So what we are doing is that we are classifying each point individually using these networks, and we take that data, use that for training, and then we can inference across US cities with a very that provide a very high scalability, while still getting a very accurate results up until the wires and the distance between the wires and vegetation and so on. The other domain is terrestrial. Terrestrial is actually a LiDAR that is being mounted usually on a car or a boat, but this is talking about a car that is driving in the utility domain, usually along the power lines that are close to the road. Such LiDAR is typically much higher density than the airborne LiDAR, around 5 to 10K points per square meter. It also has an RGB cameras on there, so it allows it to produce RGB imagery, but also colored LiDAR. And that type of data, we have a model for that separately, which can also detect classes that we talked about and enable the usages that we discussed. The third domain is the UEV, which is now becoming more and more popular. There are new cameras out there that now enable us to capture on a drone payload cameras that are has the ability to capture much more densely than before, but also has RGB in it, so it allows us to capture very recently. It allows us to capture with RGB and color. But typically, what we see today is still point cloud that has mostly intensity with it. So our model is currently enable us to take a point cloud with intensity only and provide the meaningful results, auto-classifying accurately all the objects that we discussed, including the power lines, the electric wall, utility cars, buildings, roads, and so on. And just to touch base on the first usage that I discussed, which is the vegetation encroachment. So other than the auto classification, which is nice and provides a meaningful way to show our classified data, the next step is provide some understanding per usage. So one of them is the vegetation encroachment, in which we are taking the wires that are being detected and the vegetation that is being automatically detected, and we compute the minimum distance between those two, and then we can automatically produce the risk per area and recommend on high priority areas to send the trimming crew there. I think Eric will be elaborate on that. So Eric, back to you.
Thank you, Ophir. So we've talked about the analytics and what we're doing with artificial intelligence. Now what I want to do is actually dive in and show the Intel Geospatial platform, how it manages, visualizes, and does analysis on LiDAR data. We're going to focus on one workflow. So we're going to start with a utility example in vegetation encroachment and walk through how we would do that from start to finish on the Intel Geospatial platform. Next slide. Okay, here we go. So this is the Intel Geospatial platform. It's a web-based application. On the left side, you see actually a catalog of different layers, and there's different type of spatial information in there. You'll see orthomosaic, 3D point clouds, 3D mesh, digital service models, vector data from GIS, right? So this acts as the larger catalog of all the spatial data that you're bringing together that you might use in combination with LiDAR. On the right side, we actually see a visual representation of the extent of all these different kinds of data. So every blue box represents the bounding box, or if you see the little stacked layers, those are vector layers. So we can actually determine where we have spatial data in our larger system. If we want to, we can easily add data into this system. There is both a desktop and a web-based uploader. Ophir, I think you're paused. Oh, there we go. Okay. Okay, so this is the web-based uploader. I can go ahead and enter in a layer name. So I'm going to just create my new layer, then browse to information on my desktop. It could be a LAS file, it could be many LAS files, or it could be LAS and LAS-Z's files. Select those. Go ahead and add some information about my layers. Maybe I want to add some metadata, description, who the supplier of the data is. We work with a lot of data service providers who are using this as a platform to deliver their data to customers and how it was collected. And aircraft, go ahead and click start uploading. That starts uploading into the system. And then when it's finished uploading, it becomes available in the catalog and you can display it. Once it's in the catalog, though, the question is, what do you do with it? So in the application, we actually have a workspace. And what I did, I just added the LiDAR data for Chandler, Arizona to this workspace. And I'm going to zoom into it. Workspaces are basically the places where you do work and collect multiple data sets together. This LiDAR data right now is displayed in elevation mode. Depending on what information is inside your point cloud data, you can display it in different modes. It could be RGB, it could be classified, it could be by intensity. So here, I'll flip to RGB and we can see the colored points, RGB points here. But as Afir mentioned, right, our analytic runs primarily on intensity. So I'm going to actually change my workspace to a different workspace where I have a different LiDAR data set that's captured intensity. So let's zoom in on this area. So here we have an example of LiDAR collected along a linear segment of a power system. So there's spans and poles, and they've actually flown down the electrical circuit and captured points along the electrical circuit. In this case, we're seeing intensity, but of course, if there's other views like elevation, you can see those as well. So there's an analytical tab that stores different types of analytics that you can run on different kinds of data. We're going to open the auto classifier, give it a name, pick the input data from the workspace that we're going to feed to the auto classifier and run it. It lets us know that that job has been started and is pending. You can look and see different kinds of analytic jobs that you're running and see their progress as they're going through the process over time. When an analytic is complete, the results are then automatically added to your workspace so you can visualize them. So here we see the classified LiDAR. We can see it's pulled out the electrical spans, the poles, the low, medium, and high vegetation, the ground, the buildings, right? We can expand the LiDAR layer, turn off specific classes that we're not interested in seeing, and just focus on the classes that we're interested in. In this case, medium vegetation, high vegetation, the conductors for the electrical system, and the towers. And see visually, of course, where there potentially might be encroachment or conflict. Now, it's a geospatial platform, so we can bring in additional GIS information like the spans and the towers and use those to run additional analytics. So I'm going to go back to the Analytics tab, and this time I'm going to pick the Vegetation Encroachment Analytic. Again, give my result a name and a description. Select what my appropriate input is. It's going to require a point cloud with intensity. Then use my GIS information to define where my spans are, my poles are. And then I can set some custom thresholds for assessing vegetation proximity in terms of risk. Is it within 5 feet, 10 feet, 15 feet, and the different breaks as I go from there. Run that analytic. Again, it goes into the queue, and I can track its progress. When it's done running, it automatically gets added into my workspace, and I can see where I have vegetation that's causing risk to the circuit and to the towers of my electrical distribution system here. And of course, red being more dangerous, orange less, yellow even less, and blue even less than that. So you get a thematic mapping of the encroachment along this circuit, and I can add the GIS information back in. What it's actually also doing is producing for each span, so each segment between these poles an individual risk measure that I can use as part of an inspection workflow. So here I've got a vector layer that's derived out of that. Each span listed one-to-one. I can sort those by area, by priority, by ID. I can open a span and actually conduct an inspection. Say, okay, this is listed as a high priority span. I'm actually going to say that perhaps this is not as high a priority because of the type of vegetation that's associated with this. So I'm going to give it a medium priority with a lower encroachment score, but I still want to have a remediation activity of removing the vegetation in the area. And then I'll mark this as inspected, close my inspection, and move on to the next segment. You'll notice when I updated my inspection, the colors changed on the associated lines. So this allows me to walk through my circuit and inspect step by step. If I want, in addition, I can add annotation to portions of a segment. It could be an area of concern or a distance measurement to a specific tree or specific feature that I want to call out as higher risk and capture and then share. Once I've done all my inspections, added all my annotations, right, I might want to share that. I might actually want to share a portion of the analytic directly. So for instance, I could select one of these and export that and get a CSV report on the risks associated with that span and a GIS file, a GeoJSON of that span that I could use in some third-party GIS application. Or I could actually select a span and generate a report, and actually that will give me a report with a snapshot showing me the annotations I took around that span, and share that as a PDF report with, for instance, a field crew is going to do the response. And if I wanted to, I could select multiple spans and bring them together into one large report that I could share with a field crew who's going to do the management of that spatial information. So this is sort of a brief introduction of how we would conduct this vegetation encroachment analysis, bringing in the data, using tools to do automatic classification, feeding that classification of encroachment, and then doing step-by-step inspection of the spans to generate reports and drive jobs and activities coming out of that. Okay, so the Intel Geospatial Platform. Next slide. Okay, so just to call out, you know, Afir talked a lot about the classification of it, but that last bit that we did there was the encroachment and the distance-based encroachment around the lines. Next slide. So there are a variety of other use cases and workflows built into the platform associated with utilities, also doing AI detection on top of drone captured imagery of assets as part of the distribution or transmission system, doing identification of components, doing assessment of their condition. Combining these things together, the vegetation encroachment and the asset inspection, right, creates this complete workflow around utilities and utilities management that we're trying to develop and support for our customers. Next slide. So the platform is designed to consume a variety of information, aerial imagery, satellite imagery, Lidar point clouds, inspection photos that are captured from drones or from the ground, actually ingest those and process those, help you manage those in a single location, break them out into workspaces to do real work, visualize the data, conduct analysis, and then share the results out to people who actually have to make decisions or people actually have to do work based on the analysis and the assessment that you're doing. And from our perspective, right, the Intel Geospatial platform really works on that ingestion to the sharing and reporting part of the process. And then we work with a variety of data providers who will do the flight planning, the collection, and in some cases they actually do the ingestion and processing and actually publishing of the data onto our platform. And sometimes it's the user that does that. And then with some solution providers who provide additional analytics capabilities on our platform beyond what we ourselves are building. Next slide. So in terms of management, right, you can upload your own geovisual data, imagery models, point clouds, DSMs, a variety of GIS formats, GeoJSON, KML, right? It's a place to aggregate your spatial information. You can search it and identify it. You can find addresses. You can find locations, find specific types of data, specific date ranges when data was collected, create workspaces to organize around business operations or individual teams who are conducting specific assessments, assess, document, and update your geovisual data, actually be able to edit and modify it, change its attributes. And then that's all wrapped in this ability to manage who is using your spatial data, assigning roles based on roles and responsibilities within your projects, constraining access to specific people or specific customers if you're delivering data, allowing people to actually export or download that information so that they can use it in supporting their decision making. Then once you have all your spatial data, right, very fast access to visualizing 2D and 3D data all through a browser, so it doesn't require any desktop software. Streams, massive data sets of heterogeneous 3D geospatial data. It's in 3D, so you have this immersive experience with everything on the Earth's terrain or floating above it if it's true 3D data. Being able to move between and navigate and find locations, control what's displayed, how it's displayed, changing symbology, changing display types, reordering lasers, changing colors, opacity, creating annotation on the fly inside the 3D environment so you can understand the distance between objects or call out specific areas of interest, and then creating summaries out of that to export reports so that people can take the results elsewhere. Next slide. And then being able to do analysis on your geospatial data. Where are my assets? Where are my conductors? Where are my poles? What's around them? What's the closest piece of vegetation? Is anything close enough that it's going to cause a problem? What's in service? What assets are on this pole? Does it need maintenance? Is it flashed or corroded or cracked? And what should I prioritize? Being assessed automatically by the AI, but also through the inspection process to help make decisions on the ground. And that's orchestrated through these AI-driven analytics that Intel is developing, and then recipes that our partners are developing. Next slide. So if you're interested, you can give the Intel Geospatial platform a free trial. Go to intelgeospatial.com. We have some pre-populated demonstration data, including drone imagery and LiDAR information you can work with. You can upload and manage your own data and explore different kinds of analytics that we make available, and export the results and take a look at them. So with that, I'd like to thank you, and I think we'll open it up for questions from the audience.
Sounds great, and I see that a lot of you are populating questions in, so thank you so much for submitting those. I've got a couple in the queue right now, so we'll start right off. The first one I have is, how do you get the point cloud files from the field to the cloud? Any compression software available, or are you just bringing them physically with hard drives from the field?
Yeah, we're actually uploading the LiDAR data through. We have two uploaders. We have a web uploader, which can handle data sets up to about 2 gigabytes, and you can use that to upload. Keep in mind, you can upload multiple multiple data sets over time, so you can sort of update a layer or a point cloud layer with multiple LAS files. And then we have a dedicated desktop uploader, which doesn't have a file size limit on what it can handle, and it uploads over time. So you sort of set it as a batch task to upload information to get that online. Ophir, is there anything you wanted to add to that?
No, that was pretty accurate.
Okay.
The next question we have is, does the platform do Lidar post-processing from coupling GNSS, IMU, Inertial Explorer, flight line corrections, incorporating GCPs, etc.?
So, Mark, let me answer that. Currently, our platform assumes that the LiDAR is already post-processed in a way that each and every vendor and LiDAR camera has its own processing procedure that best fit the optics and the hardware in place. So we really prefer to take the LiDAR file in the form of either PCD or LAS or LAS or any other popular LiDAR format that is already processed and for the specific hardware and customer need.
Sounds good. And how long does auto classification of a typical LiDAR dataset take?
So since those networks can handle the challenges that I specified, for example, the sparse of the data, we now have methods to overcome that. We see a great benefit in those algorithms, and not only we are able to process the LiDAR directly, we are able to do that pretty efficiently in terms of memory access and so on. And using GPUs on our cloud, on our platform, we are able to process multiple kilometers, let's say more than 20 square kilometers per night. So we see that in practice we are able to take multi-kilometers data from our customers, and with a very short time afterwards, we're able to provide the results to the customer.
Great. And with your vegetation classification algorithms that you showed today, are you able to provide segmented results for different tree species?
Mark, do you want to take that? So I'll take that. No, currently our model, the LiDAR model that we are displaying here does not identify between tree species. There are other channels that are better than that, RGB channels or multi-spectral channels that are much better than LiDAR to identify tree species, and we tend to leverage that, but that's a different scope and a different analytics.
Yeah, you would have to break that apart and use the multispectral information to do subsetting of the LiDAR where there is coincidence, but it would only be 2D. You'd basically be doing 2D subsets by species type, not point by point.
And is this system SAS-based, or can it be installed on your own web server or your own secure web server?
Yeah, this is all software as a service. It's not on-prem at this time.
Are there other roadway asset automation tools that you have in the system? Signs, shoulders, guardrails, those types of things?
Yeah, there's actually a company that Intel owns called Mobileye. They do vehicle navigation, hardware and software. And they also, through that hardware, do collection of road assets. One of the things that they're doing is extracting out of that segmentation information for roads. So being able to identify the lanes, the curbs, the curb heights, the distance, the sidewalks, assets along the roads, and then also usage information. So if the sensors can see pedestrians and bicyclists, it can catalog those and catalog their frequency. And then because it's a navigation system, also doing some tracking of vehicle behavior. So for instance, if it sees a defect in the road like a pothole, and then also has multiple vehicles that are swerving or braking hard, it can actually assign a risk associated with that. So it's a different, it is sort of still computer vision based, but produced by a separate part of the company and a separate data set, but is available on the Intel Geospatial platform.
And is there a specific or a minimum point cloud density that you have found works best for this feature identification?
So the different LiDAR sources are varied with the point density. I can say that we have experience with a relatively low density, for example, 15 points per square meter until thousands of points per square meter. That really depends on the object that we want to capture, how small they are or how thin they are. For example, for wires, we do see that the minimum is around 20 points per square meter. We can maybe go down to 15 or 10 points per square meter, but not less than that. But for example, vegetation, we can go even lower. And obviously, we have no maximum, no limit on the density on the maximum input density. We can always downsample if required.
Never can go wrong with more points, right?
Exactly.
All right. And what is the accuracy rate of auto classification? How much time on average is needed to manually adjust afterwards?
So we do our best to avoid any manual fixes, and we at least in our on our popular use cases and our popular object. I can say that generally in the AI systems, we will never get into 100%. We'll always try to be on 100%, but we'll never get there. It'll always be in 99.999, something like that. We do see that with our AI models and some automatic post-processing, outlier removals, and so on, that are more tailored for a specific use case, we are able to get to a customer experience where there is very, very little to no manual fixing afterwards. But it really depends on the usage and the object. There are objects like wires, vegetation, cars, and so on, where we have a very high accuracy. There are other objects that are more less common or more smaller or complex in other terms that we are still struggling to get sufficient accuracy.
And can this platform take in data that was collected via drone? Or autonomous?
Yeah, as I mentioned, our third usage was actually UAV, which is a drone, and also what Eric was demonstrating was drone data. So a drone is typically is a very, very good tool for capturing either, for example, power lines that are not close to road, or if we want to have closer inspection. So drones are very popular these days, and we have a lot of experience in processing and inferencing AI on drone data, both in intensity only or including RGB.
And are you able to process photogrammetry generated point clouds?
Can you elaborate on that? What do you mean geometry point cloud? Do you
Oh,
mean
no, I'm sorry. Can you process photogrammetry generated point clouds? Sorry.
currently we're not optimized to do that. We are more focused on the Lidar use case. Photogrammetry Lidar is typically much less denser, so it has its own challenges. So currently we are not focused on that.
Great. Okay. And sorry, there's a lot of quick questions in here, so hold on, let me grab another one here. Is it possible for a user to create their own model with classes for specific system types or signature, or is this something that's managed on Intel's end?
So the answer is pretty complex because on one hand, no, we cannot easily integrate new object. What requires typically is annotation and additional annotation and training, because the way that we are doing that, the training is a supervised way. We need supportive data, and we need that annotated in order to train the system and support new object. So so that's the process. But on the other hand, if the user has that capability already, we can, as Eric mentioned, our platform is open to loading the customer analytic on the platform.
Okay, great. And I think I'll take one more question and then we'll wrap up here. Okay, a couple of these are asking kind of the same thing about the kind of minimum resolution, but we did cover that for the density of the point clouds. Let me see here. Besides this kind of reporting that you get, are exports of the LiDAR or other artifacts supported?
Yeah, you can download the classified LiDAR. If you need to do some additional editing and cleanup of the classified LiDAR, you can take that down out of the system and do that in a third-party package. And likewise, the vector data that's produced from that, the encroachment data, you can actually take that out as GeoJSON as well.
Great. And actually, I'll have one more question, is that if someone's interested in kind of working with you on developing something that works for them, what's the best way to get in touch? What should they do first? Should they do a free trial? Should they contact directly? Is there a specific place they should go?
Yeah, I mean, I think start with the trial, and you can reach out directly to myself, eric.winter@intel.com. Or Mark Christian, I think it's mark1.christian at intel.com, and we can definitely have a conversation with you.
Great. And I see a few logistical questions that I'm just about to answer too as we wrap up here, but I want to thank Eric and Ophir, and actually Mark as well. He was in there answering some of your questions in the Q&A box, for joining us from Intel Geospatial today, and thank you again to Intel for your support of today's event. This webinar was recorded, so if you missed any of it or came in late, you're going to get an email in a couple of days that tells you exactly where and how you can watch that again. And we will be also sending out those on materials that will include a copy of this presentation as well, so that you can get a little bit of a closer look up at that data. We are always eager to receive your feedback, so when you leave this webinar, there's going to be a really short little survey about how it went. If you take a second to fill that out, we do appreciate that, and we do look at those. So if there's anything we can do better next time, we want to make it a positive experience for you guys. And then last but not least, if your questions weren't answered at this point, we're also going to turn the questions over to the presenters, so they may follow up with you as well if you had a more specific question. So thank you so much for joining us for today's webinar, and thanks again to our presenters for such an interesting presentation today.